All right, welcome back. Today we'll talk about the boot sector primarily, but in order to understand the boot sector, which is also going to be our homework, we need to know a little bit more about assembly addressing modes in particular, but also the various execution modes that the x86 CPU is capable of. So before we get there, we should sort of get into the routine here. We'll take a quick look at the solution for the homework. There really isn't much to it for this one. And then at some point we'll talk about the next homework, which is due on the next Tuesday. So let's see what I have first. Let's see, what's it called? Yeah. In fact, I haven't looked at this, but let's see. Oh, look at that. Do I actually have floating number in there? Okay, sorry. Looks like I didn't make a solution. Can't very well talk about that one then. All right, so we'll have to talk more abstractly about the solution. And there was one thing that kind of tripped people up, and that's this thing that you have to have an exit at the end, or you get a trap 14. So this trap 14, it says, oh, you try to access some memory that you're not allowed to access. But we just stopped running, and so what's like the function finished? Why are we accessing memory suddenly? What's going on? Any ideas? Why do we get a memory access error when our function is finished? There's no more instructions to run, right? Yeah?
Does it try to return from main and go to whatever address is already on the stack?
Exactly. So at the very end of our function, why don't we try this? Oh, doesn't even compile. Perhaps it compiles in inside of x86. Let's try this. All right. Well, that's not great either. Let's just kill this one for now. Okay, here we are. So this is 64-bit assembly. It looks a little bit different than what you might. In fact, you were doing 64-bit as well. I keep forgetting that we're in 64-bit now in this version of the class. So here's a typical beginning of a function, right? The function starts over here. Here's our main. You declare main in C. It ends up being a symbol in assembly. Looking at this, label in assembly. So we're storing the old RBP value and so on. Right? When we called main, because every function gets called, whoever called main puts the return address on the stack, and then we run our assembly instructions. Not all of this is actually assembly. This is some annotations that aren't really actual instructions. But here we are, some more instructions. We run all this. Here we actually call printf. We come back from printf, do some more whatever, eventually get rid of the RBP that we put on the stack, which we put on the stack over here. And then there's a ret. And what ret does is look at the top of the stack, basically where RSP is pointing now. It's expecting a return address. And so now we get a ret, and we try to jump to that return address. And what's on our stack? Well, it's a little unclear. It could be that we are going past whatever memory we can access, so even the stack is inaccessible. Most likely the stack is, whatever byte we're trying to access is still, we're allowed to access it. But then there's a bunch of zeros there or something. And so now ret is going to jump to address 0, and we certainly can't do that. We can't access address 0, and therefore we get a page fault. So in a normal libc environment, there's another function, start, that calls main. When main returns to start then calls exit, which kills the process. And killing the process, that's a system call. You get into the OS, but you never get back out. So you never get to do this kind of faulty return. Okay, so in terms of printing out the decimals, I'm hoping it wasn't too complicated. The general idea is, divide by 10, then divide by 100, see if there's anything left. Or multiply, is it? Multiply by 100? Anyway, just that sort of thing. I'm not going to go through that solution, I think. So the whole point of this exercise was not really to write this divide program that's like a CS111 material, but to see, can we get this into the make file? What's the difference between having something running in Linux and running inside of x86? And just basically getting x86 to build and having the right environment. So if you all got your divide to run inside of the x86 window, not in Linux, then we're good to go. All right, who got it to run? Okay, we're in pretty good shape then, I think. All right, so let's take a look at a boot sector then. In fact, we talked about maybe we'll just write the boot sector actually. So what BIOS does when it first loads your boot sector, it's looking through all of the disks it knows about, reads the first sector. Yeah?
So I was not able to turn in my homework. It's showing that the repository is not found.
Well, too bad. So the homeworks are due at 3:30, unfortunately. And okay, so where was I? Right. So BIOS loads the first sector of the first disk, makes sure that it's actually a boot sector, and then starts running. So if we want to make our own boot sector, we'll have to first construct that 512 bytes, and then pretty much just point QEMU at the file containing those 512 bytes, and it'll just run. So let's see what we can do. Let's see. All right, so we'll have to do this in Linux. Where's my Linux console? Here. Too many windows. It's always like that. All right, so now we're going to just write a little bit of assembly. Usually we don't need to write so much assembly, but for a boot sector you don't have a choice. There's some little things like running BIOS routines that you just can't do from C. Any ideas? Why can't you call a BIOS routine from C? BIOS routines are these things that kind of read from disk and write to the screen and get a key from the keyboard.
The motherboard's memory itself?
Well, every C program is also on the motherboard. I mean, everything is in memory. BIOS routines are actually no special kind of memory. The way it works is it's sitting in flash, yes, but upon boot, it's read into RAM, and from there on, it's just some code in memory. There's nothing special about the BIOS parts of memory. There's a whole bunch of assembly there, a bunch of machine code that we don't know exactly how it works. Right? Of course, we can read the source code for it, but we don't need to know exactly how it works. It's just you make this int 16, right? And now it does whatever int 16 is supposed to do. The problem, of course, is there's no way to write this int instruction in C, right? Int is a assembly thing. C has assignments and pluses and function calls, but it doesn't have interrupts. So there's just no way to express it. All right, let's get started on this. So first, we want this to be a 16-bit program. So we have to tell the compiler what we're going to be in 16-bit. So there's actually some slight differences. Sorry, not the compiler, the assembler here. There's some slight differences in how the assembler interprets what you write, depending on which mode you want to be in. So you have to tell it this, and now it'll produce the right machine code. Now they're actually quite similar. 16-bit, 32-bit, 64-bit mode, they're quite similar. 64-bit has all the same instructions that 16-bit has, plus a few hundred more, right? And many more different variations of each. All right, so we need, so I don't know that we need a start label. Let's forget about that. Why not? This could be handy for later. Okay, so now we want to call, let's say we want to put something on the screen. How do we put something on the screen? We need to use one of those interrupts. So let's try to Google for that. And I'm doing this kind of live because I think you'll have a similar experience over the coming week. So BIOS interrupt write. Perhaps in 13, could that be good? Oh no, this is for reading to the disk. Reading from the disk, that's not good. Maybe it's, I'll just go like this. In 10, that sounds familiar. Okay. So this is the right one. Int 10 does all sorts of stuff with the screen. 13 does all sorts of stuff with the disk. So in this case, we wanted to write a character to the screen. Okay. A, that looks pretty good. So write a character only at cursor position. Attributes, this is colors. Basically, you can also say, oh, this should be like a blue character, but we'll stick with this. Okay, so we need int 10. And then we need some parameters to it. So what was it? We need a move. This was A, was it? Yeah. Actually, let's see what else there was. This is the one I've been using in the past. Why don't we try this E instead? So to AH. All right, so what am I doing here? Do you know what the difference is between a dollar and no dollar? Yeah. Yeah, this is an immediate value. I'm saying put the value E into AH as opposed to put whatever value is stored at address E into AH. So if we go like that, it's going to be reading from memory at a very low address. The 13th byte number 13 in memory. All right, but we want an E there. Okay, and then I think we need to put in. Here, actually, I can choose. I can say move, or I can say move B. Actually, will produce the same output because here it's implicit. AH is a 8-bit register, and so it's a move B by default. But why don't we be a little explicit? While we're at it, AH is actually the same thing as AX. Here. Intel, let's see, x86 quick start guide. All right, here's our AH, and then AL equals AX. So this is the high 8 bits of a 16-bit register and the low 8 bits of a 16-bit register that equals the 16-bit register itself, AX. So this is register A, and there's BX, there's CX, DX, right? And so it goes the same way, BL, CL, and so on. And then, okay, so here's, call this 8-bit versus 16-bit. And then if you want a 32-bit name, it goes EAX, and 64-bit goes RAX. It's all the same register. There's one A. And so if you store something to AL, it'll change the 8 lowest order bits in RAX. RAX is only available in a 64-bit mode. Okay, going back to the code. What did we need? We need to we need a character in EL. Which character do we want? Let's put a U for UIC, or an X for XV6, X in AL. Same thing here. So this is a character literal. The assembler will just translate that into the ASCII number for X, for capital X. So I need to put $, here, otherwise it'll try to read from address X, which doesn't make any sense. Okay, I needed some more parameters. It wants a page. I don't think we need to worry about pages, and a color. And that we probably need to worry about. Let's see if there's... Here we are. Let's go with magenta 5. Okay. So in BH, so now I'll go like this. 5 BX. So what did I do here? Actually, let me write it a little nicer. So here I'm saying, okay, let's move this as a 16-bit value at the same time, and move a 5 to BX. So this means the same thing as that, right? Which in turn means the same as moving 0 to BH and then 5 to BL. Why am I doing all this low-level nitty-gritty stuff? First of all, I don't have a choice. If we're going to do a boot sector, there's no other way to do it. But I'm also spending a lot of time on this because we're going to see a bunch of assembly throughout the semester here, and we need to kind of get a little comfortable with what all these things are. And at least this is a kind of easy setting. Okay. So now we've written our parameter values. I don't think we need anything more. We should have a magenta character on the screen. But unfortunately, it's going to crash. Or it's going to do weird stuff. We don't actually know what it's going to do after this. Probably reboot. Why? What do you think? Why would this machine reboot with this boot sector? It's such a nice boot sector.
Because it doesn't know
Any sequence for a boot sector is not present.
Ah, very good. We did need that AA55 at the end. That's a good one. That's not why it's going to crash, but it wouldn't even crash actually. It would just say, oh, there's no OS, and then it would stop. So we need to, okay, let's do that one first. And it goes something like, we want to tell it that at the very end, you say org, that's just how you do it. You say like, where does, like move the cursor in the binary here down. We want to put it at the end, 512 bytes, minus 2, right? So we could say 510, but you know, we're computer scientists, so why don't we do it in hex? So we'll do 1FE.
Why minus 2?
Because we also need to put some bytes in there. So we'll say, right? So if I put it at 200, 512, then it would end up in the next sector, right? So we want it at the end of our current sector. All right. So this is 510, right? That bit is worth 256, and then FF would be 255 minus 1. There we are. Okay. But now it's going to crash. Actually, why don't we try that? So now we need to build this thing. This is should be pretty straightforward. Let's see. So called testboot.s. Ooh. Okay, what's this all about? Operand size mismatch for int. Any ideas? Oh. I don't know why my nano is so weird.
Just use them.
Yeah, I hate Vim. Usually, I mean, I don't edit code in Nano normally. I would never suggest that you do. That's the only sort of thing that I don't like do the same way I do at home on the screen. I use Nano because it kind of isolates everything. I don't have, in Emacs, I have 100 different buffers open. I don't know which version it is. It gets a little more self-contained this way, but when it's dropping a character in the beginning, it's really no good. See, there should be a period there. And there, it isn't there. But yeah, okay. So, what? Fine. All right, so what's going on here? It's complaining. Yeah?
Is it looking at BL and saying that you're going to BX instead, so that's 16?
No, I was complaining about this line with the int. Dollar, exactly. I'm telling it int whatever is at that address. Right? And int doesn't read from memory anyway, so it doesn't know what we're talking about here. There's no instruction that reads an interrupt number from memory. So we'll have to tell it which interrupt number. Oop. Gotta love this garbage. Let's see.
If you're in Vim, press
I know, it doesn't do it.
This is VA. Oh, okay. Function delete.
So I am in mode. Wow, gotta love this. Okay, let's try my Mac Nano, see if it's any better. I'm gonna have. I think there's something wrong with my console. I don't know. I've had this for a while. Let's see. For executes public. Okay. Anyway, it'll probably be fine. Let's try this. So we're going to compile this thing. AS. Okay. So now I made an object file. Now, unfortunately, these object files, they're much bigger than 512 bytes. It's 1200 bytes. Why? What's that?
Debug symbols?
Debug symbols? No. Well, it's possible, but it would still be too big, even if I stripped out the debug symbols, if there are any in there.
It's using a lot of stuff that isn't really required.
This is an object file. It starts out with an elf header, right? And then it has probably some other things. Let's see what's in there. Read elf is a fantastic little tool. This is all the stuff that's in this 1200 byte file, and we just want the code, right? We don't care about what sections there are in this program and all these other things. So we just want to pull out the code itself, and we can do that with object copy. Actually, before we do that, let's do a disassemble of this. Okay, there it is. Oh, it's a little short. Ah, yeah. Look at that. That doesn't look right. What's this? We didn't write any of this, did we? Right, we did write an E to AH. That's pretty good. The rest? Aha, that's the
ASCII.
that's the ASCII of X. So that's pretty good. But what is this? I said 5 to EBX to EX, right? BX. And now it's saying whatever garbage to EBX.
I mean, the last 5 bytes are still fine. The last byte is still 5.
Yeah, okay, so it might actually work. It's not so bad. Yeah, but it looks a little confusing. Yeah.
Is it because we didn't write zeros between the last 2 bytes and the last instruction?
Oh, our program is right. But this is wrong. We didn't tell the assembler. Well, we did tell the assembler, but I guess somehow inside of this .o file, it still figures we wanted a 64-bit binary. But the assembler actually did the right thing. We just have to tell it that this is 8086 code. I think it's, I8086. There we are. Okay, that's pretty good. So now we have those 4 lines that we wrote, almost exactly what we wrote. And then, what's that? First, there's a whole bunch of this. Dot, dot, dot. There's zeros in between here. And then finally, we have an add. Where'd that come from, do you think?
It's reading the 558A and interpreting it as a command.
Very good. This assembler output here actually puts the machine code right here. You see move is B4, actually move to AH is B4. And here's the value, the immediate value E. Okay? And here we have a move to AL, that looks like it's B8. No,
That's 58.
B0, right? And a 58 is right there, okay. And so on. Okay, then it got a little more complicated. This one got a little longer, right? Because we had a wide move, a 16-bit move. So we need 2 values, 2 bytes for the immediate value. And it's yet another one here. Which is a different instruction for every kind of flavor of these moves. Okay, and then we have our int 10, and then 55AA. And what's that? Well, that is add DL to minus 56 in DI. Right. But so my only point here is there's no difference between instructions and data. Right. The assembler, disassembler in this case, and the processor has no idea what you meant. It'll just do whatever you said. You said 5588, that's what it means if you try to execute it. If you try to copy it somewhere, you try to put it on the screen, it's something different, right? But it's just bytes in memory. There's no way to tell that these are executable bytes. We can sort of tell. People can sort of tell. You disassemble something and you see, okay, that kind of fits my pattern, my idea of what a function should look like. It should start with a push EBP, you know. There's lots of opcodes that are instructions that I recognize. And the machine will just do whatever you tell it. Okay, so we were going to run this thing. Object dump. I think it goes like this. No, it's O binary. So I'm telling I want output format binary. Right. So we're going to read our test boot.o and stick it in test boot.img. What happened? What's this? Invalid option. Oh, that's good. Should it be a little o? Obju dump. Oh. What is it? Oh, it's called object jump is what we use for copying. It's called object copy. Object jump is for disassembly. Okay. Here we are. All right. So so now this pulled out just the binary code, not the headers and everything. We just get the raw bits from in there. So now if we do a hex dump of our testboot.img, we should be see something familiar. 0EB4, 58B0, 05BB, right? And end with AA55. That's exactly what we saw before in our disassembly. I think we can do an object dump. Let's see if we can do this. Never mind. I think that we can disassemble that too, but I'm not familiar with the. I love it. Let's try it. Do we have to tell it what kind of? Yeah, I don't know how you tell it that this is just raw data and or raw binary code. But anyway, we have our image, and so the disk is relatively small, right? This is our disk image. Hopefully 512 bytes. Yes. So now we just have to tell QEMU to boot using this disk. So we'll do that. For comfort, I will do it in here. And there it is, an X. It's a small X, but there you are. Okay. So, in fact, it didn't crash very well. I don't know why it didn't crash. Oh. Yeah. So after this int instruction, there's a bunch of zeros. And I guess those zeros were okay. And then came this other add thing. And then I think it's still running zeros. And probably all of memory is full of zeros. And I don't know what happens when it runs out of memory. Every time I've seen this before, it's crashed. Either way, we probably wanted to, just stop running instead of just running a bunch of random code. So how do we make it stop running, do you think? Any ideas?
Just add a return instruction.
A return instruction. Very good. Return to where? No, I'm just messing you. There's no place to return to. Now the BIOS, could conceivably have called the boot sector and left a return address on a stack, but that's not what it does. It just copies the stuff into the right place in memory and jumps to it, and then it's hands off.
The boot sector is supposed to load the operating system.
That would be nice, yeah, but we don't know how to do that yet. And so if we just wanted to stop running, here's one way to do it. Right?
Isn't that an infinite loop?
Exactly. And so now we know which instructions it's going to run. It's going to run jump. That's it. So at least it's not going to do the weird stuff. But let's take a look at this, because it's not entirely obvious. Let's see. And we'll see an interesting little test boot. So right, so this looks fine. What's it doing? Well, okay, so we got that same. In fact, And here's a little trick. I hit Control R on the bash command line, if you haven't done it before. And then I type in some letters. 80 I typed in. It's searching in my command history for 80, and I found this one. All right. It'll save you a lot of time over the next many years. All right. So I hit enter. Oop. And it was a bad one. Okay. -D. It's like that, wasn't it? Yeah. All right. So this looks good. Stop is at 9. Right, that's the label. So I'm jumping to 9. Okay, fine. So let's try running this. I'll copy it out. I run it with QEMU. Oh, we can't even tell the difference. It's being so nice, this program. I guess I have a later version of QEMU or something, and it's just behaving a little better, which unfortunately isn't great for demonstrations always. So it's actually not jumping to the right place. So just to make this a little more clear, let's do it this way instead. I'll jump to start. It is jumping to the right place. Holy crap. I guess so much for that. So, okay, fine. I was going to demonstrate that this is an absolute jump to address 0. And we're actually, all this gets loaded to 7C00, so it's not supposed to work. But it's full of zeros all the way from 0 all the way to 7C00, so it's actually still working. How do I demonstrate this not working? I don't know. Yeah.
Do you know why it's not magenta?
Why is it not magenta?
Yeah,
That is a very good question. That is a very good question. Probably got them in the wrong order, didn't I? No. Color in BL. Where is it? Teletype output. Color in BL. Only in graphic mode. We're probably not in graphic mode, in fact. Yeah. That's, yeah. Okay, so anyway, now I'm not 100% sure that we run into this problem, so we'll ignore it for now. But basically, if you try an absolute address, without an example, there's no way to describe this. So this is doing a relative jump. It's not jumping. I'm not sure actually. How do we test this? Okay. All right, let's do it like this. All right, now let's see if it prints out a bunch of Y's. So my theory here is that this jumps to address 9, right? Because it said jump 9. At address 9, there's nothing for us. So it shouldn't work. Because this one is at 7C09. And for whatever reason, it still worked. So let's try this. Compile it, copy it, run it. Yeah. So it looks like that's a relative jump then. I'm going to have to look into this myself. I don't actually know why that worked. I'll send a report. Yeah.
I was going to say, I've had this issue before, but when you copy it to a USB, it'll crash in the real device. For some reason, I think like Kimo allows you to do that. So aren't you supposed to add like a little header on top to say that your code starts at?
Yeah, exactly. So you should link it at 7C00, but for whatever reason, it decides it works anyway. And maybe Kimo is being very nice. That could be it. All right, it doesn't matter. So this is one way that we can talk to the hardware. Right? I wanted to put something on the screen. Well, how did it end up on the screen? We just asked the BIOS to do it. But there's nothing special about BIOS. Right? BIOS is just code. The only thing there's a couple of things that's special about it. To run the function, you don't say call function name. Right? You do this whole int thing with the registers and stuff. And that's just how they set it up back then, and maybe it seemed easier back then. And the other thing that's special is that it's coming from Flash, but it's sitting in memory now. It was loaded from Flash automatically, but now it's sitting in memory. Other than that, there's nothing special about this bit of code. So in principle, we should be able to talk directly to the hardware as well. We don't need to ask BIOS to do this work for us. And it so happens that the console, the text display, is pretty easy to talk to directly. So I thought we'd try that too. So here, the way this works is we have the screen is represented by bytes. There's 2 bytes per character. They're sitting at a certain address, well, we'll find it in the x86 sources. And so just a big array of 2-byte entries represents all the characters on the screen. If you change one, the monitor or the graphics card sees the change and updates the screen. So all we have to do is go and write to that part of memory. So let's see what how that works in x86, and now I'm going to give up on Nano because we have a little too much code to look at. So this is the boot sector in x86, doesn't matter. Let's take a look at console.c. Console is the graphics driver, the screen driver in x86. So whenever you want to write a character to the console inside of x86, you'll be using these functions. CGA put C. CGA is a color graphics adapter. It's a very old standard for the screen, which we still use for normal text output, and a character. So all I wanted to see is how does it end up on the screen? And we do a lot of this in sort of in systems programming. There's a lot of like, how do these people do it? Then I can do it, right? Because the documentation is seldom very good. The code is better documentation than the documentation itself. So how do they write something to the screen? Well, here it is. Well, that's a space being written out. Here we're writing a character. So we're writing to the CRT array. What's CRT? It's right up here. And this is what we need. So that's the address of the CGA memory. If you write to that address and below, and above, I should say, like B8 and up, we'll see characters on the screen. Looks simple enough, so let's try that. So instead of this, we'll say move B and let's see. I'm pretty happy with the Y. We'll keep that. And we'll say move B AL to, and then that address. Thank you. All right. And in fact, let's try it this way. So I don't get to write move by directly to the address only because there is no such machine code instruction that takes immediates and writes to memory. So I put it in an intermediate register and then I move it over. So let's try this one out, and we'll ignore the fact that it's doing this loop and writing it over and over. It's writing to the same address, so it won't cause any problems. So let's compile that. Ooh, now we got a warning. I think we have to pay attention to these warnings. So on line 9, something got shortened. Here's line 9. This address is too long. We're in 16-bit mode. We don't even get to write addresses that long. 16 bits, how many of these nibbles is that? A nibble is 1 hexadecimal character. 4. Right? Each nibble represents 4 bits. You know, it goes from 0 to F, so that's 16 combinations, meaning 4 bits. But that address is 20 bits, right? It's 5 of these nibbles. But we still need to write to there. But we can't express addresses that large. So this is a little weird. We have a 16-bit machine, and the graphics adapter is sitting way above the 16-bit address range. How many bytes of RAM can we address with 16 bits of address, you think? 2 to the power of 16. Anyone want to take a guess? What's the number? $65,536. I only remember because I used to work on this 16-bit machine. Oh, come on. Doesn't it not show? It doesn't actually show that number. I must remember it from somewhere else. Anyway, so with a 16-bit address, we can specify 65,000 different addresses. So we can only actually access 65K of memory. This was fine when they first designed the i8088, right? The 8-bit machine, which happened to have 16 bits worth of address space, because even for them, it would have been annoying to have only 256 bits of address, 256 bytes of address. So they had 16-bit address range. That was fine, but then they made the new machine 8086, and they figured, well, maybe 65K isn't enough for everyone, so they came up with a clever fix. Instead of going beyond 16 bits of address, because that was a big change, to change the architecture to 32-bit, which they could have done, I suppose, they introduced this thing called segments. So when we first boot up, we end up in 16-bit. It's called real mode. This also uses segmented addressing. Every address consists of 2 pieces. It's a segment, like where my code is. I specify a segment, and then the offset into the segment. So it goes segment : offset. There's an implied offset here. Implied segment. If you have a jump, it implies that I want to jump within my code segment. And if it's a data access, like move, I want to access something within my data segment, unless I specify explicitly which segment I want to talk to. So you say like this. If you want to be explicit, you say code segment 6. Move code segment 6 to AX. And now it's getting the 6th byte out of the code segment. And here we get to specify then up to 65,536. That's the offset inside of the code segment. So the way we can now access our graphics memory is to provide a new segment. We say, oh, the graphics segment, we'll just use the ES register for it. E is just another like auxiliary segment we can use. So I'll say move B8 to ES. Okay, so here I'm saying, okay, there's a new segment I will be using sometimes, ES. It's at this address, but and plus another 0 at the end. Segments just kind of shave off the last 0. So you still deal with only 16-bit values. There's an implied extra 0 at the end. So that's the beginning of my segment, like really with another 0 over there. And now I can specify my address as segment colon offset. So I say ES colon, and then the offset is nothing right now. So the beginning of the segment. So again, the math then becomes, you know, ES shift by 4 plus offset. Right? So I'm saying, okay, read from segment ES. That's at this address, but you know, with an extra 0, so I've shifted 4 bits, it's an extra 0. And then offset bytes into that segment. So a segment really isn't, you know, a chunk of memory that's isolated from anything else. It's just this math. That's all there is to it. You get to add these numbers together. But what's nice about it is that it adds 4 more bits of address space. So now we can address up to 20 bits of memory, meaning 1 megabyte. So that's our maximum address space right now. Okay, so let's try this out. And I'm not 100% sure it's going to work, because I don't remember what where the color bit goes and where the character bit goes. So, or color byte and character byte. So we'll try this, see if it works out. Oh, instructions suffix. What's wrong with it? Aha. Yeah. Same thing going on here. AX. Okay, that should be okay. Run it. Yeah. So maybe I was just in fact, I wrote to number 0, right? The 0th byte in our character array. You see it? There's the Y. So we could do a little better. Let's, while we're doing assembly hacking here, let's try something else. So I'll say Alright. I guess it'll get upset maybe at some point, but let's see. Oh, bad memory opera. Oh. Not very familiar with this syntax. There it is. Okay. Okay, so I wrote Y, and I keep writing, like, now I'm writing to the value inside of BX. I'm not saying, okay, write to BX. Write to the address that BX is pointing at, right? That's what the parentheses mean here. And I'm writing out a whole bunch of Ys, but you remember I said it's 2 bytes per character. One is the color. That's why we end up with magenta here. And so as a background, you actually get both a background and a foreground. So let's change that to, and you get to play with all of this pretty soon. So run it again. All right. So now I was just writing the character bytes and not the color bytes, and got a little more sensible. Okay. So there's a little crash course in assembly. Let's take a quick look at the homework description. Basically, we're writing a boot sector. It's going to be a little bit nicer than this one. In fact, let's check out my solution first, just how it works. So this is part of the solution. You should be able to say make bootsplash.img in Linux. It produces this image file, and then we call, and we run it with bootsplash, and it displays a nice little message, UIC rocks, and then I hit enter because we're waiting for an input. We got a screen, a graphic screen. That's the homework. So it involves a few different pieces, right? You print out a string, not just a character. We did a little bit of a string, just a bunch of Ys, but you can do better than that. And then there was waiting for input. Right? It's another BIOS call for that. Then we switched modes to graphics mode. It's another BIOS call. And then we read in something from the disk, this picture, and put that in the graphics buffer. Now we were writing directly to the character buffer at B8000, and now the graphics buffer is at A0000. Not so different. So we need to convince the BIOS to read in this whole image from the disk. And then of course you have to actually make your disk. The image is provided. This is, I don't know if any one of you knows Edmund Zalensky. No, he took the class last semester. We had a really ugly picture, but he made this one. So I credit him for that. All right. So let's take a quick look at the homework description. Right. So the first thing you need to do is create this disk. Starting out, you're fine with just the 512 bytes like we were doing, but later on you'll want to have the image on the disk as well, that picture. The picture is in a file called cover.raw. I think it's somewhere here. And so you'll need to copy in the 64,000 bytes that this image consists of. Just put those after the 512 bytes of boot sector in your image. There's two kinds of images here, right? The disk image and the picture image, and it gets confusing. Anyway, you can use this tool DD for it. That's what it's for. It's a disk duplicator. It exists in every Linux distribution. It's convenient. All right, and then you're writing to the screen, you're changing video modes. Now, you definitely want to change video mode first, and then read in stuff from the disk. We're reading this image from the disk, right? Because when you change video modes, the graphics card automatically clears out the entire video buffer. So if you read it in from disk and then switch, well, now it's going to be black all the time and you'll be disappointed. So I would change to the right video mode and then just write a few characters into this address. Or bytes, that is. Whatever bytes you write probably will show, unless it's zeros, probably will show up as some colored dots on the screen up in the left-hand corner. It's not going to get pretty if you do it that way. Next up, we'll use some BIOS services to read in the contents of the disk. So you need to read in a whole bunch of sectors, right? There's 64,000 bytes exactly. Divide by 512 and you know how many sectors you need to read in. So what we have to do is tell this BIOS call the address to write to, which sectors to read, like which sector to start reading at, how many sectors to read, and where it should go. Right? And maybe from which disk. So there's a whole bunch of parameters there. And the way this works, it's a little extra complicated because there's too many parameters. They don't really fit in the registers. The parameters are relatively large. Like a disk sector is described in more than 16 bits. There can be very many sectors on a disk. So the way this works is you put, this is int13, right? Put 42 hex. There's another syntax for hexadecimal. It's not familiar. Put 42 hex in AH, and now it knows, okay, you want to read from the disk. What are we doing? The drive number in DL, and then ignore this packet. They call it a packet, but it's just a struct on this, in memory. So at this address, you recognize this colon syntax here? In DS, we have part of the address. In SI, we have the other part, because it's sitting somewhere, depending on where you put it. We have to be able to describe a 20-bit address. Probably you can just put zeros in DS. Okay, so now you need to put the location of the rest of the information in memory in this combination here. I would put zeros here and then the address of your struct, which will be within the 512 bytes on the boot sector in SI. Okay, and then finally, there's a disk address packet, which is a bit of a beast. So you have to use, just like we did, in fact, we didn't, but let me demonstrate. You do have a relatively nice skeleton to work with here. In your make file, it looks like this. This one builds an image for you. And then we have this boot scale. You're supposed to make one called boot splash, right? But this is the template. In bootscale.s, this types out the first character of this string. So we're saying H. Right? We're moving the value at this address into AL, and that's the first byte in the string. All right. So using similar syntax here, there's stuff like .byte, .word, .quad, .long, I think. You can create this struct here. So you put a byte with the size of the packet, a byte with a 0 in it, a word with the number of blocks, figure out how many, put that number in there, and so on. And the hardest part is this. Well, I guess these two are both a little bit tricky. Here's the block number, right? It's 8. How many is it? A Q word. So that is 8 bytes. It should just have a 1 in it, but you have to put the 1 in the right place. Right? It's the byte order. So it's little endian. The 1 should come first. And here for the transfer buffer, it comes in this. Is it described anywhere? It's let's see. it's better described somewhere else, I think. It's better described in the homework description. Basically, here we have a 4-byte, a D word is 4 bytes. We have a 4-byte address, but a 4-byte address has to be segment and offset like any other address in 16-bit mode. So you have to describe your address in segment offset notation in there. If we go back to the homework description, I think it says in some more detail how to do it. Right, so it goes offset first and then segment. It looks like so. The first 2 bytes are the offset. Second 2 bytes are the segment. You may want to Google a little bit on this int13 AH48 to make sure you get this right. That one's gonna you're gonna stumble on that one quite a bit. Okay, this actually brings us to maybe the last point here. If we want to test things in GDB, you're gonna have to use GDB in this class. I know there's always some people who say, no, I can do it without, and you can manage relatively far in, and then eventually it just takes so much time that you can't handle it, and then it's over. Much better to get started with GDB today and use it for every homework. Here's how you run GDB. If you're in Linux, make QEMU GDB. All right, so now we're running this with okay, and I need another console. And I say GDB. All right, so now I'm running QEMU. If I say, oh, this is a little small, isn't it? At the very beginning of the boot sector, it stopped. I think it's the beginning of the boot sector. Entry.s, that doesn't look like it. Okay, so I say continue, and then it starts running into x86. But we want to play with a boot sector, so it's going to be a little bit different. So here I say let's do it from Linux. Here. What was it called? Boot test. Test boot. .img. -s minus capital S. All right. So you see the emulator has stopped and is waiting for GDB to connect. And it's waiting on some port, and I think we can, it's localhost 1234 if I remember correctly. So if I do this manually, I'll go GDB. Oh. I would do it in here. Target, remote, localhost 1234, and we're connected. Okay, so right now the QEMU here is waiting for the program for GDB to tell it to continue running. Right? You can say continue, it'll be like debugging any other program, except we're kind of debugging what the virtual machine is doing. It's kind of a strange debugger situation. We're not running a program, we're connected to a program inside of another machine, but it kind of feels the same. You're debugging the whole machine. So I'll put a breakpoint. What was it? It was called test boot. Boot test. Oh. Okay, so I told it to read the symbols from this object file. The symbols say where all those labels are. In our assembly case, we had a start and a stop, I think. If it's a C object file, every function has its own one of these labels that you can put a stop for. So I'll say break at start. In fact, that's address 0. That's not going to work. At last, the linker problem shows up. Remember I was saying 7C00, that's what we should be jumping to, and we were jumping to 0 and it still worked. Well, this is not going to work. Let's try it. In fact, let's go like this. So I put a breakpoint 2 at 7C00 as well. That's nice syntax. See, asterisk and then an address, and that'll help us go directly to some address if that's what we want. Okay, so I'll continue and we'll see where it stops. Okay. So I guess QEMU loads the boot sector at address 000.
Does it let you do the layout in GDB?
The layout.
Yeah, normally in GDB you can do like layout ASM to CD assembly specifically.
Layout, I don't know, but I can disassemble. If that's what you mean.
It does the same thing, but shows you the program counter and the actual code and it steps down.
Ah, I'm not familiar with this. I'll have to check it out.
From the actual C source called layout SRC or layout ASM for assembly.
Oh, interesting. I think we can tell it like this. In fact, it doesn't know how long it is, so we'll have to use X. This is a cool little thing too. I'll say I want 10 instructions printed from starting at this address. Well, that isn't exactly what we had over there. Doesn't look quite right. That's yes, those are our instructions. Sort of. We're in the wrong architecture. Let's see if it was like that. Oh, yes, that looks much better. So you'll run into this too, right? Right now we're running in 16-bit mode. GDB needs to know which mode we're actually running in, and so you have to tell it. Otherwise you get this weird, confusing stuff. Anyway, so I don't know how GDB decided that this is breakpoint 1 at address 0 when we're actually at, it's even pointing at that address here. And if we say info registers, look, EIP, that's the instruction pointer. We're at that address. So somehow, QEMU is just trying to screw up my classes. Okay, so now we can step, one step at a time. Maybe we can't. Next then, can't even do that. Next instruction, thank you. Step instruction. So let's just see. Right, so it's slowly progressing, and now we should see that AH has a different content. Right. In fact, EAX has a 5 in it right now. Let's put something else in it. Let's see what's in it now. Was it AH that we wrote the E to? Yeah. So there it is. Okay. So you'll need this. You'll need the X to print out both instructions. If I say how many, and then I say that I want instructions. I can also say I want characters, I want to say. Let's see. All right, now I get them like that. Maybe I can get bytes. Oh, it's the same thing. Hexadecimal output. Right, you'll find this very useful. What happens if we go hexadecimal words? Right. So this will actually help you a little bit figure out the byte order thing too, right? How see how this shows up first? B4 shows up first, but here it's after because it's little endian first. So make sure you kind of inspect your current state. try printing out the contents in the graphics buffer at the A0000. Try printing out what your disk address packet looks like in GDB to make sure you actually got what you thought that you put in there. There's a lot of little things here. It'll be good practice for when we start playing with stacks and things for thread implementations later on in the semester. All right, that's it. Get started early. Bring lots of questions to class next time, and we'll get through this together.
Before you close that, can you try typing the layout ASM?
Oh, layout ASM.
Yeah.
Oh.
You do SI and then you can actually walk the step.
Very cool. Thank you. Very nice.
You can layout REG for registers to see how the registers change with each instruction. I'm pretty sure you can even overlay those two layouts like that.
Wow. Okay, I'm learning something new here. Very good. All right, and that's even recorded, so now everyone gets it. Cool, thanks.